Hello and welcome to a new recording on mathematics for machine learning. In this recording we are going to discuss the topic of automatic differentiation. What is the automatic differentiation? It is a numerical method for differentiating different formulas with respect to one variable or more than one variable. This is different from a symbolic differentiation, which is regular in high school calculus courses, where you do the mechanical steps yourself or manually with human intelligence. Computers need a more numerical method to perform this sort of operations. So the formula for differentiation of f of x with respect to x, the limit when h or the step is infinitesimally small, and then we've got f of x plus h minus f of x divided by h. So you can see two problems with this formula. We can't apply this formula on the computer for two reasons. If h is infinitesimally small as it is supposed to be, then we are going to run into a float over flow arithmetic operation problem, and then if we set h to be larger than this very small value, we are not going to get an exact answer. So that's going to be an approximation, a very bad approximation. The solution is to use either automatic differentiation or finite element method. However, there is a problem with the second solution. The finite element method could be quite slow when it comes to processing large vectors and large matrices. So the automatic differentiation is the right choice. It can operate in two modes. One is the forward mode and the other is the reverse mode. The reverse mode is more optimal in terms of runtime complexity analysis. That means it is rather faster than the forward mode. However, it is quite tricky a little bit, just in terms of the steps of the operations. It is very similar to the forward mode with just very small slight changes. That's why let's start to review the forward mode for this automatic differentiation operation. Let's say that we want to calculate the partial derivative for a function of two variables, f of x of y, which equals cosine x sine y plus x over y. So first we have to construct the graph, a cyclic directed acyclic graph, that the graph of the operations. The operations are going to be the nodes and the variables are going to be the leaves of the graphs. The graph will have the operations of such as primitives, multiplication, addition, division, and so on. We start at the node. The node over here is the addition operation, and then on the right hand side we have a multiplication operation which has got two operands. The first is cosine operation and the second is a sine operation, and finally we've got the input cosine of x and sine of y. On the other side of that directed graph we've got a division operation with two operands. The first is again x and the second is y. So this is our directed acyclic graph. As you can see, there are no cycles in the graph, and the runtime of the automatic differentiation algorithm is going to be linear in the number of nodes of the graph, with some polynomial constant which cannot be found in the case of the reverse method for automatic differentiation. So let's give the nodes some symbols to make our life easier. We'll call this omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, and finally omega 7. So to calculate the differentiation with respect to two variables of this function, we want to do it like this: differentiation of x and y relative to both x and y. That means we have to do partial derivative, and that's quite different because you have to do the derivative relative to one variable, leave the other as constant, then do the other thing. And there is a quite formula for this, where for example if the derivative of a function x multiplied by y, that's x derivative y plus derivative x multiplied by y. Quite familiar if with high school calculus, you find this quite easy. Just the idea here is that we have to represent these nodes in the similar graph. So for example, how do we run this operation? We start with, from the bottom, d omega 1, which is, when we are doing it with relative to variable x, that means y is constant. So with d omega 1 relative to x equals 1, and d omega 2 relative to x is 0, since y is constant. So that was the first level. The second level, we have got to do the d omega 3 relative to x. Remember, we are doing the derivative relative to x. Cosine x derivative of a cosine is a sine, and derivative of d4, derivative of sine is minus cosine. Oh, here we were about to make a mistake. Remember, this is a sine of y. We are derivative relative to x. So this one becomes again 0. And then d omega 6. Here it's getting rather tricky since this is a multiplication. So that will be what we have said. The first variable with the derivative of the second derivative of the first. So relative to x, cosine x sine y, that will be omega 3 d omega 4 plus omega 4 d omega 3. So we have got omega 3 sine x, we have got d omega 4 0, and omega 3 itself was the cosine of x. So this becomes cosine x multiplied by 0, it goes away. So this factor is eliminated, and then omega 4, which is a sine y, multiplied by d omega 3 sine x. And then we've got to do d omega 5. Remember that with division, the equation is rather different. That is d omega 5 omega 1 over omega 2, that becomes omega 1 d omega 2 minus omega 2 d omega 1 over omega 2 squared. We have got omega 1 d omega 1, and so on. We continue with the graph till we reach the root node. We do that relative to x one time, and the other time we do it relative to y. And this is the basic of the automatic differentiation algorithm in the forward mode. In the backward mode, we do the same operations, but instead of starting with the bottom or the leaf nodes, We start with the root node and end when we reach the leaf nodes. Quite different from the first approach in that it runs faster, strictly linear time, which is very good for machine learning. So why have we discussed these very low level details of mathematics when it comes to automatic differentiation? It is already implemented in NumPy, in PyTorch, in TensorFlow. You hardly have to do this operation yourself. However, in many real-life situations, when I myself have been in one of them, we have to dig deeper into the differentiation operations, since we are trying to modify them, tweak them according to some advanced machine learning algorithms that we have been using, that are unorthodox and unusual algorithms that have been in some research papers, some of our own algorithms, and that's why we had to dig that deep and change the internals of this TensorFlow library